This is going to be section 12.3 Integrated Math 2, and we've been working with quadratics. So please make note of some of the things that we're going to be focusing on here. We're going to be working with domain and range of all of these quadratic functions. And I'm not going to lie, sometimes this is a little bit difficult. We're going to be determining x-intercepts. We are going to be finding zeros, and we're also going to be determining intervals of increase and decrease. So where it's going up and where it's going down. So you can kind of see what we're going to be doing here. All of these terms are going to be brand new to us. First one, it says we've got a model rocket. So this is kind of a projectile motion problem. So let's go ahead and read through this together. It says here, suppose you launch a model rocket from the ground. You can model the motion of the rocket by using a vertical motion model. A vertical motion model is a quadratic equation that models the height of an object at a given time. The equation is in this form right here. Right? So this is what you're going to have to get used to. Where g of t represents the height of an object in feet, t represents the time, we have this v sub 0, that is going to represent initial velocity, okay, initial vertical velocity, and this h sub 0 is going to represent our initial height, wherever this object is starting from, its starting height, okay. Now, it's asking us here, why do you think it makes sense that this situation is modeled by a quadratic function? Well, take a moment. I mean, why do you think so? If I were to draw this, let's just say I have I'm going to work in right now quadrant 1 just for a moment, because that's kind of where reality takes place, right? Well, we have, let's talk about this. Isn't that the shape of a problem? Certainly is. Well, in this case, you would have two things happening. Time would be over here, okay, and then your height, or I like to call it h of t, but they call it g of t. There's your height. And if you're kind of traveling along this, let's get a little old smiley face. Throw it up here. If you're traveling along this, here's where you would be launched from. You're going to launch your rocket. Okay, notice it's launched. It's not launched on the ground. If that's the case, it's down here. It's going to be launched right here up in the air, maybe on the top of a building, something. Launches up, then it comes back down and hits the ground. That's what we're talking about. That's why a parabola, a quadratic function, is a great function for modeling projectile motion. Number 2, suppose the model rocket has an initial velocity of 160 feet per second. Okay, let's get out highlighter, 160 feet per second. That is our initial velocity. V sub 0 is equal to 160 feet per second. Important information. It says, write a function g of t to describe the height of the model rocket in terms of time t. All right, so here's what we have. G of t is equal to negative 16 t squared plus v sub 0 t plus h sub 0. We just have to kind of take the information we're given and let's substitute it in. Here we go. G at t is equal to negative 16 t squared plus, well, look, initial velocity is 160 t plus, now they did not indicate at all here, it says the model rocket with initial velocity, so it actually doesn't indicate here that it has an initial height at all. So I'm going to assume that it's going to be 0 for now. We're going to shoot this or launch this rocket right from the ground. Okay. Now, I will say in a normal situation, they will tell you that h sub 0 is equal to 0. That's important to know. It's launched from the ground. It says describe the independent and dependent quantities. All right, so let's break this apart. Let's go with independent first. Remember, independent is like input. What are you going to put into the function? Well, we're going to put time. And specifically, time here is going to be measured in seconds. You can see it right here, seconds. Dependent variable. Well, consider your dependent like your output. Well, if you put in time, look what comes out. You plug in time here, you plug in time, you get your calculations, and look what it gives you. It gives you a height at a specific time. So we have the dependent is going to be, it's going to be g at t, or g, right? There's your, let me give you the quantities here instead of the variables. This is going to be height. And the height is specifically measured in feet. And they do have variables. The independent variable would be t. So this would be your t variable. And down here, your dependent would be g at t. Okay? All right, I hope that kind of makes sense. We're just launching just a projectile motion problem. All right, number 4. Number 4 asks us, it says, use a graphing calculator. All right, let me make sure you're following me here. Use a graphing calculator to graph the function. Sketch the graph and label its axes. All right, we can do that. Take out a graphing calculator. And you can pause the video and just try to beat me to it. It's totally fine. Here we go. All right. So head up into y equals, and I have negative 16 x squared. Remember, there's no t, so, and then plus 160x. Looks like I have it correct here. And let's go ahead and graph. Oh boy, I have a weird window happening from maybe another example that I've done in the past. So I need to do some fixing here. I've got to figure out what kind of window I need to use. Well, for now, I've got this projectile motion problem, so why don't I go ahead and take this max. Let's change this max. I'm just going to change it to 100. Then let's see what happens when I graph this out. I still can't see the top of this thing, but I see it coming back down. All right, I'm going to take the window, and it looks like, let's head down. I'm going to make it 500 and see what happens. Oops. There we go. And graph. Aha, now I can see the entire parabola. There it is. All right. Let's pull this in so you have an accurate graph. Okay. There we go. And I did leave this in here so that I could connect it and you could see what was happening. And you'll notice, again, I would have to adjust my window on there. But I'm not really concerned about that. They asked us to use a graphing calculator, so we're good with this right here. Let's move down. It says, use a graphing calculator to answer each question. What is the height of the model rocket at 6 seconds? Okay. Need to make this nice and large. We're going to be using this a lot. Okay, it's 6 seconds. I'm just curious, when I did graph these, are these going by ones? Well, to check that, go up into my calculator, head up to Window, and take a look. My X scale is going by 1, so I'm good to go. All right, so this happens to be 1, 2, 3, 4, 5, and 6. All right, so kind of follow me here. I'm going to get an arrow going. If I go over to 6 and then straight up, that point right there, okay, let's put a little smiley face at it, right there. That should represent 6 comma something. I'll put a question mark, 6 comma something. All right, so what is the height of the model rocket at 6 seconds? Well, take out your calculator, and there are a couple ways to do this. You could trace, or easiest way, second, calculate. See where it says value right here? Number 1, value. Select number 1, and let's plug in 6. Enter. Ah, there it is. Okay, there it is. You have, let's erase this. Let's make sure it's nice and neat here. We have 6 comma 384. All right, so there is the height. So the height here, we can reveal this answer. There it is, 384 feet. Moving down, after approximately how many seconds is the model rocket at a height of 200 feet? All right, keep in mind, we're looking for seconds. We are looking for time. Time equals question mark. I don't know what that's going to be, but I do know that we're at a height of 200 feet. Now, this goes back to Integrated Math 1, where you were finding some intersections. So let's take a moment and open this calculator up. All right. And I want you to be able to see the large screen here. So let's go ahead and do that. Let's open that up. There we go. And remember, we're trying to find the time when this thing is at 200 feet. So let's just leave it right there so you can see the 200 feet. Y equals. I'm going to come down. Well, what do you think I'm going to graph right here? 200. When I graph this out, look at what it gives me. That's a height of 200. And what's really important to see here is that it's actually going to reach a height of 200 how many times? Well, it's going to reach it once on its way up. It reaches it, it goes up, 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 reaches its maximum, comes back down, and then it actually reaches 200 feet high again. So we've got to find out what those values are. All right, here we go. Second, trace, intersect, number 5. And I can find this one first. I'm already pretty close to it. So enter, enter, enter. And the intersection happens to be 8.54 seconds. 8.54 seconds. All right, so one of these is at 8.45 seconds. Oops. That should be 8.54 seconds. Okay, and the other one, second, trace, head over to intersect, number 5. Let me get close to that point. There we go. Enter, enter, enter. And that looks like at 1.46 seconds. All right. So I'm going to move these down here. At both of these times, you reach a height of 200 feet. I hope that completely makes sense. Definitely with the graph. All right, it's asking for here, what is the maximum height of the model rocket? And when is the rocket at its maximum height? So in this first question, let me underline that. You've got to be really specific with what they're asking. What is the maximum height? Okay, so in red right here, they're looking for feet. They're looking for height. in feet. But in the second question, when is the rocket at a maximum? They are looking for time right there. So they're looking for time in seconds. So be careful. We want two different things here. Head over to the graph. And I'm going to do second trace. Let's get the large calculator going so you can see what's happening. There we go. I'm going to select maximum, number 4. And I'm going to head up kind of close to it. They're asking me for a left bound. Okay? And the left bound, they see where it says right here? There it is. Left bound, hit enter. Head over to the right of the point that you're seeking. Somewhere over there, it doesn't matter. Enter, enter. All right, there is your maximum. And keep in mind, you have two things here. This is the time it took to get to the max. So at 5 seconds, the rocket was at 400 feet in the air. All right, so at 5 seconds, the rocket was, I believe they said right here, 400. Yeah, 400, okay. Up in the air. Number 6, you can use a graphing calculator and intersection points to determine the x-intercepts of a quadratic function. Oh boy! All right, so we've got another task here. X-intercepts. It says what linear function can you graph along with the quadratic function to determine the x-intercepts? Explain your reasoning. All right, that's a pretty deep question right now. They're asking for another linear function that you can graph along with the quadratic function. All right. Let's open up your calculator. And let's head up. I'm going to just get rid of this 200 for now. Clear that out. We're done with that. Well, head back to the graph. Here's the large one. And here's ultimately what I'm going to be looking for. I need to make sure that I'm pretty consistent and I go nice and slow through this so you understand what I'm talking about. All right. The x-intercepts. There is one right here, and there is one right here. So an x-intercept is where this blue graph is going to intersect or intercept the x-axis. You've got this x-axis here, and here's your y-axis. So we need to be able to find those two. Now here's the question they're asking. What is the equation of the x-axis? Well, that equation is a horizontal line, and that happens to be y equals 0. So we can graph that also on the graphing calculator. Let's take out our calculator and give it a shot. Okay, so I'm going to go over here, y equals, head down. I'm going to just plot 0. Watch what happens. There it is. Now, second trace, and I want to intersect number 5. Let's intersect. I'm going to get over to that and x-intercept close to it. Enter, enter, enter. There it is. There's one x-intercept, and that happens to be 10, 0. The other one happens to be, let's go second, calculate, intersect number 5. I need to head back over near that one. All right, enter, enter, enter. That happens to be 0, 0. Now, hopefully you understand that in this problem situation, this means, okay, this point just means that at time equals 0, height is equal to 0. That's what that means. Now over here, at time equals 10 seconds, the height is equal to 0 feet. And think about it. What does this mean then? The object went up, came back down, and it took 10 seconds before it landed back on the ground. There it is. It says determine the x-intercepts of g of t, then interpret the meaning in terms of this problem situation. We just completely did that. Okay, there they are. We already talked about that. It says the x-intercepts of the graph of the function here, so you can follow me here. It says the x-intercepts of the graph of the quadratic function are also called the zeros of the quadratic function. Okay, I can't stress that enough. Let's make sure that you can see. Zeros, very, extremely important. You need to understand that zeros are really x-intercepts. There's a slight difference, however, we'll assume that they're the same. Zeros and x-intercepts are the same for now. All right, I'm going to teach you another method to find a zero on the calculator. Watch this. Okay, open up the calculator. And I'm going to head up into y equals, and I'm just going to get rid of this 0 right here. Clear that out. All right, the only thing I have is the quadratic. You can see it. There you go. Graph. Now, second trace. Oops, second trace. There we go. And look what comes up. 0. That's how you find x-intercepts. Select number 2. And it's asking for a left bound. Well, let's try to find this one right here. Okay, so I can hit enter right here. That's on the left of the point I'm seeking. Now let's go to the right. Okay, now you can't see it right here. There it is. There's the cursor. If I keep going down, I'm going to go down below, but I'm still going to be to the right. So here's my right bound. Enter. There it is, 10, 0. Okay. And for the other one, second trace. Number 2 is a 0. They're asking for a left bound. Just hold this button down. Let's get over there first. Let's get to the left. Okay, I'm at the left. You can kind of see where I am. I'm at x is negative 0.07. That's where I am, underneath here. Okay, enter. Come up to the right of it. Enter one more time. And there's another 0, 0, 0. So that's another way of finding x-intercepts. Number 7. 7 says, identify and describe the domain of the function in terms of the mathematical function you graphed. Okay, for this function that we graphed, okay, there it is. I'm hoping that you do see that we can go to the right forever, and we are going to go to the left forever. Now, I know it looks like we're going down, but we're still going down to the right, down to the right. And over here, we're going to go down to the left, so we're still going left and right forever. So the domain is going to be absolutely all real numbers here, all real numbers. Now, within the context of the problem, within real life, reality, we are only going to be able to deal with these x values. Notice where I'm highlighting, only in between here. That's it. So from 0 to, well, we know what that point is over there. This point right here happens to be 10. So from 0 to 10. Okay. Now, I want to actually write it a little differently there. One way to write that is that your domain, your x, can be less than or equal to 10, or it can be greater than or equal to 0. That's one way of writing that. That's a compound inequality. Identify and describe the range of the function in terms of the mathematical function you graphed. Oh boy, the range. Okay, let's do this again. All right, so pay attention for a moment. Pay attention. In yellow, this would be the domain. Got it? That's the domain. Let me write that here. The domain is from 0 to 10. Okay, from here to here. But if we're going to talk about range, the range is how high and low this function exists. Well, it starts at 0 and then goes all the way up to, well, didn't we find the maximum? Right here? What was that maximum? Well, that maximum was 400. So the range is all real numbers less than or equal to 400. So that your y values are less than or equal to 400. Okay? And keep in mind, for this range, I didn't say this just now, but the range, just for the mathematical situation, it's going to keep going down forever. That's why it's going to be all real numbers that are less than or equal to 400. But in the context, do you think that this, whatever we're going to fire up in the air and come back down, is it going to go below the ground? No. So your range is going to start at 0 and only go up to 400. Okay? And another way of writing this, you can pause the video if you want to read that, but the y value has to be less than or equal to 400, but in context, in reality, greater than or equal to 0. Starts on the ground, up to its maximum, back down on the ground. And it says here, how is the range of the quadratic function related to the absolute maximum or the minimum? Well, as far as the range is concerned, we have the absolute maximum or the minimum of that quadratic function completely limits this range, doesn't it? Because if you look at the graph up here, it has to go from 0 all the way up to 400. Okay, on this next page, this is going to be maybe a little challenging. This is called interval notation. Interval notation. And I need to describe this very well to you. You'll be definitely tested on this. All right, an interval is just a certain set of numbers in between two numbers, okay? We've got a certain notation to go over here. Open interval. Notice, the open interval uses parentheses. Then we have this closed interval, and notice it uses brackets. And finally, a half-closed or half-open interval uses a combination of a parenthesis and a bracket. All right. Now, important, let me highlight this. Intervals that are unbounded, meaning they just go on and on and on forever, can be written with this symbol, the infinity symbol. All right, we're going to do some practicing here for a moment. Okay? And it's going to be a little abstract, so just pay attention. I might use a number line if I think you might need it. Let's try number 10. It says, use interval notation to describe the interval in which are all numbers that are less than a. All right, what if I do this? If I give you a number line right here, and let's just say this right here is a. Okay, that's the position of a on a number line, and we're looking for all numbers that are less than a. That would mean that I would be highlighting the numbers that are strictly less than. Now ask yourself, is A less than A? No, it's not. So what we do is we use a parenthesis, okay? And we're talking about all numbers to the left. So think about this. If I continue to go to the left, just watch my cursor. If I go to the left, do you agree if I keep going to the left, then I'm going to go to negative infinity? So the way that we write this is this. This interval here is from negative infinity, and we always use a parenthesis for negative infinity because there's no end to negative infinity. And then all the way up to A. But are we including A? We are not. So this is going to be another parenthesis. Okay? Once again, let's just erase this. Let's just explain it again. All right. So I have from negative infinity all the way up to A, but I'm not including A because it has to be strictly less than. So there's your answer for A. Let's look at B. All numbers that are less than or equal to A. Well, now, if I get a number line, there we go. Sometimes it helps to draw this out. Here is your A. And if I'm talking about all numbers that are less than or equal to it, well, it's going to be actually this point plus everything to the left. Now, because it's going to be equal to it, we're going to use a bracket. So the correct way to do this is going to be from negative infinity, and keep in mind, whenever you're going to use an infinity, negative or positive, there's no end to it, so it's an open parenthesis, all the way to A, and I bet you know what I'm going to draw right here, not a parenthesis, but a bracket. This means, in what we call interval notation, all numbers that are less than or equal to A. Okay? Let's move down to C. A is any real number. All right, so if I get number line going, it means that A can be actually anywhere on this number line. Anywhere. Doesn't matter. So it can be anything. Well, it can go to negative infinity or it could go to positive infinity. And here's how we write this. From negative infinity to positive infinity. And you know we're going to not use a bracket but a parenthesis on both of them. That means all real numbers. All real numbers. Number 11. I hope that made sense, folks. Number 11 here. Use interval notation to describe the interval of the domain in which the model rocket function is increasing. All right. I'm going to get this graph out. Here it is. Let's pull it onto the smart board. Okay. There we go. And let's actually put this up here for now. We are going to be talking about the interval in which this thing is going to be increasing. All right. Let me use some highlighting. Let's go with, how about where it's increasing, I'm going to highlight in yellow. So this thing is increasing, meaning from left to right, it's going up, 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 up. It's increasing, 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 and probably stops around right there. Okay? There's my increasing. Now my decreasing, let's use green. Here's my decreasing because it's going to be going down from left to right. Let's talk about these intervals. Okay, there's your kind of breakpoint there. So it's increasing from 0 all the way to, well, we use the x-axis to describe that. So here's 0, and we know that it's somewhere around this area here. So that's going to be okay, I just kind of quickly put this other picture up here so that I could show you what the maximum was. And it looks like this is going to be at a maximum height of 400 and that looks like it's at 5 seconds. So let's label this with a 5. I hope you agree that right inside here that it's increasing from 0 to 5. Okay, increasing from 0 to 5. Now look where it's decreasing. It's decreasing from 5, but all the way to, and this was 10. Okay, so from 5 to 10. Now, the way that I have this written right here, we are not done at all. But you'll notice that I'm actually using our contextual, our reality here, our real setting in order to describe where it's going to be increasing and where it's going to be decreasing. Now, if we were just working with this quadratic and there were no rocket was being launched at all, then there might be a different scenario here. It would be increasing because this would keep going down. It would be increasing from negative infinity all the way up to 5. Okay? And then it would be decreasing from 5 all the way to infinity. But in our situation, our contextual situation, it's increasing from 0 to 5 and then 5 to 10. All right? Our next page, problem number 2, intervals of increase and decrease. We're going to be given a bunch of examples, and we're going to figure out all these important pieces here. Domain, range, y-intercept, zeros, intervals of increase, interval of decrease. So let's begin here. Here's my first graph. Negative 2x squared plus 4x. Now you can pause this video and plug that in if you feel like into your graphing calculator. But here's the graph of it. Okay, there's no contextual situation, there's no real life situation, it's just a graph, a mathematical graph. We have a domain. Do you agree it's going to go left forever and right forever? So the domain is going to be all real numbers. Okay, the range. The range is actually, we're talking about up and down, all right? Well, for this example, it's going to begin as high as 2, and then it's actually going to go down forever. All right. If you were if you were riding on this, it would look like this. You could go up, 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 and that's the highest you would be at, and then you would go down forever and ever and ever. So the range is all numbers that are less than or equal to, less than or equal to 2. Okay. My y-intercept, look at where my y-intercept is, 0, 0. The zeros happen to be my x-intercepts. Keep that in mind. This is x-intercepts. All right, I have one right here. That's a y-intercept and an x-intercept. So that's a 0. But this is also a 0. It's going to be 2, 0. Intervals of increase. Well, notice, how about we do this? Here is my interval of increase, and up to that point, okay? And that is going to be from negative infinity all the way up to, well, look, it's increasing, increasing, increasing. It's going up, 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 all the way until, what's that number? That's all the way until 1. Now it's going to be decreasing, and follow me here, decreasing from 1, and remember, and when we're describing intervals, we use the x values. So it's going to be from 1 to infinity. So from 1 to positive infinity. You might be asking, well, when are we going to use a bracket? Well, when we're describing intervals of increase and decrease, think about it. At 1, right here, at 1. Is it increasing or is it decreasing? It's actually technically constant right at that certain point. So it's neither increasing or decreasing, so we have to use this, this parenthesis instead of a bracket for this interval of increase and decrease. And there they are. Moving ahead to this one. All right, I'm going to be asking you how to do these. Let's, domain. All real numbers. It's going to go left and right forever, okay? Up to the right, up to the left. Range. Well, you kind of really have to pay attention here. You kind of see this is going to come down, and I wonder how low that comes down. Well, it looks like it's probably going to be around, well, if this is going by ones, this is 1, that's going to be 0.5. That looks like it's 0.25, or maybe down a quarter. So it could start at down a quarter, -1/4, and then go up forever. So all real numbers that are greater than or equal to -1/4. Y-intercept. Look at this. It's got a y-intercept. The y-intercept is right there. That is 0, 6. And let's talk about zeros. For zeros, I see a 0 here, and I also see a 0 right there. Looks like those zeros are -3, 0, and -2, 0. Interval of increase and decrease. Okay, so be careful here. Let's interval of decrease. That's going to be right here. And it goes down, down, it's decreasing, decreasing. There it is. Increase would be right here. Okay. So I would say that it's going to be decreasing from -infinity all the way up to, well, what's this point right here? That looks like it's -1, -2. Here's your -3. So that looks like it's -2.5. So that's where it's decreasing. That's where it's going down. Now it's going to be going up, increase. So that's from -2.5 all the way to infinity. Next one. All right, the graph shown represents this function. Domain. All real numbers. Range. Okay, look at it down here. Look at the range. Be careful. Range is all real numbers greater than or equal to -2.25. Y-intercept. Well, y-intercept is right here. Look at it. What point is that? 0, -2. Zeros. Okay, so these zeros are going to be here and here. Remember, zeros are x-intercepts, here and here. What are they? There they are. Interval of decrease. Now, I already know that this is going to be the most difficult. Okay, some of you get it, and it's fine. But interval of decrease, it's going down from here all the way up into here. So the interval might be easy if I do this. What if I use, it's decreasing from this side all the way up until right there. Okay? And that value seems to look like it's going to be 0.5. So it's decreasing from -infinity all the way up to 1/2 or 0.5. All right. Now it looks like it's going to be increasing on this interval right here, forever and ever. So it's increasing from 0.5 all the way to infinity. We'll reveal those, and there you go. This next one is going to be the last one in the video. Okay. Domain. Domain, it's going to go left and right forever, so we've got all real numbers there. And range. Range. Look how low this is going to go right there. Look how low it's going to go. You have to be really careful here. Very, very careful. It looks like it's 0, doesn't it? Doesn't it look like it's it just goes up from 0 and then up? Well, you best be really careful. Why don't we take out a calculator? Turn that on and head up into y equals and clear that out. This is going to be x squared plus 11x and then plus 30. And let's go ahead and graph this. I need to probably set my window. I can see where this whole window is going to be. Let's move this over. So I'm going to set this window up to 40, out to negative 15. All right, so x max, let's just make that 5. X min, I'm going to go back up to x min, and let's make that negative, how about negative 14. Y min, negative 5 is fine. And y max, let's go up to 40. Let's go ahead and graph that now. Now, I don't know about you, but to me that looked like it dipped right below the x-axis, just for a brief moment. So let's see what we can do there. I'm going to find that minimum. So second trace, let's find the minimum, number 3. Let's surround this thing. It's looking for a left bound. So I'm going to get to the left of the point I'm seeking. Enter. Now I'm going to get to the right of the point I'm seeking. Enter. Enter. There is the minimum. And folks, look at what that says. Look right here. It goes down to negative 1/4, negative 0.25. All right, so negative. That point right there is negative 5.5 comma negative 0.25. That's going to actually give us our range. All right, hopefully you're kind of following along. This thing's going to come down, and the lowest point it's going to go to is 0.25 and come back up. So your range is all real numbers greater than or equal to negative 1/4. Y-intercept. Oh boy, so look at those y-intercepts. You might need to graph for this. You might need to look at this graph. And how about, let's make this nice and large for you to see. Okay. And we're looking for a y-intercept. Well, I guess the y-intercept is pretty easy to see. We don't even really need much there. The y-intercept here is just going to be 0, 30. You can see it. It's right here. But the zeros might be more difficult. Let's find these zeros. So second trace, I'm going to find the zeros, number 2. Head over to where you think it is. Close. Enter. 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 Oh, I didn't do that correctly. Number 1, quit that. And second, calculate. Once again, let's find the zeros again. My left bound, let's get to the left. My right bound, that's good right there. There. It's negative 6 comma 0. So that point right there is negative 6 comma 0. And I would imagine that you can guess that that one is negative 5 comma 0. There are your zeros. Interval of decrease. Okay, so on this interval right here, it's decreasing, 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 all the way up to right there. So let me move this. Looks like it's decreasing from negative infinity all the way up to negative 5.5. Then it's going to be increasing from negative 5.5 to infinity. And there you have it. And look at this, negative 11 halves is really negative 5.5. That concludes our section 12.3.